Hello, Algebra 1 class. Today you're going to learn about something called the correlation coefficient. This has to do with scatter plots and lines of best fit. Take a minute and look over the learning targets for this lesson. In this warm-up, you want to take a look at the 4 scatter plots, and you want to write down which one doesn't belong and, of course, your reasons why. Go ahead and pause it now and do that. Okay, hopefully you chose one. I'm going to go through each one and talk about maybe some of the reasons you wrote down. So in the first one, you have distance in terms of cost, or cost in terms of distance. And you can see that this is a fairly strong linear model because they're all tight together. And it is increasing. So you might have chosen for that because it's the only one that's such a strong linear model that is increasing. In B, we have the weight of something in terms of its height, and you can see it's all over the board. So this one does not have a strong linear model that you could use. So maybe you chose that one. In C, we have the water used for irrigation in thousands of gallons in terms of precipitation. And we can see that this is a decreasing model because it's coming down. And it's also a pretty strong linear model. So maybe you chose that one because it's the only one decreasing. And in D, this one, it's increasing like A, but this one's increasing at what you might call an exponential rate. It starts going up slowly and then increases much quicker. And that is not a linear model. So hopefully you chose one, and why you chose it was one of those reasons. In this activity, you have 10 scatter plots with drawn-in linear models, and they're on this slide and the next 2 slides. So hopefully you have the document file with you so you can pause it and try to answer the questions before I go over it. But what you're going to be asked to do is sort the cards into 2 categories. So you have to look at all 10 scatter plots and make a decision about which one belongs in bucket A versus bucket B. And you decide what creates those buckets, or explain the meaning of your categories. Once you're done that, then I'm going to have you mix them all up again and come up with 2 new splits or buckets that you can put them in. So why don't you pause the video, open the file, or you can also watch the video for the next 2 slides, make some decisions going back and forth about your first set of buckets and then your second set of buckets. Here is the next set of cards. And here is the last set of cards. Okay, which buckets did you choose? The first group that I saw to separate them is the ones that were very linear and the ones that were a nonlinear model. So if you go back and look at the different scatter plots, the linear ones were C, D, F, and G, and the nonlinear ones were A, B, E, H, I, and J. So that's one set of splits that you could have done. Another set of splits that you could have done were scatter plots that were increasing versus decreasing. And of course, there were some scatter plots that were nonlinear, that were neither increasing or decreasing. So we have our increasing, and these were E, F, G, and I, and those decreasing were A, C, D, and J. And of course, those that were neither were B and H. See how you did. Okay, once you've checked over your work, now I want you to go look at them again. Notice for each scatter plot, you have a linear model listed in y equals mx plus b form, as well as something called an R value. The R value is the correlation coefficient, which we're specifically going to talk about now. So I want you to just look at all 10 scatter plots and what their R values are versus the scatter plot. See if you can make any determinations just by looking at the 10 and their R values as to what values you have for R, what's the range of approximate values, when are they positive, when are they negative, when are they large, and when are they small. All right, let's talk a little bit about what the correlation coefficient is. First of all, when you use Desmos or any other graphing technology that allows you to find a line of best fit, you can ask it to calculate the correlation coefficient as well. And this is usually designated by the value R. So R is a number between -1 and 1. That describes the strength and direction of a linear association between two variables. The sign of the correlation coefficient is the same as the sign of the slope of the best fit line. And the closer the correlation coefficient is to 0, the weaker the linear relationship. When the correlation coefficient is closer to 1 or -1, the linear model fits the data better. The closer the R value is to 1 or -1, the better the linear model. So in these examples, you can see here, this is an increasing linear model. So this value is very close to +1. The middle graph is a very poor linear model. You can see the scatter plots very wide apart from the line. It is increasing though. So this is closer to 0, but positive. And the last model is a very good decreasing linear model. So this is very close to -1. So once again, the R value goes from -1 to 0 to 1. This is a good positive. This is a good negative. And this is not good. Closer to 0. Here is a nice summary for you talking about the correlation coefficient and scatter plots in general. So remember back in earlier lessons we talked about the plot of the residual values. Those can help pick the best line to fit the data among many lines, but we still needed a way to determine the strength of a linear relationship. Scatter plots of data that are close to the best fit line are better modeled by the line than scatter plots of data that are farther from the line. The better the model, the more likely its predicted values can be used or will be useful. So it's important to know how good your linear model is. So, while it is possible to try to fit a linear model to any data, you should always look at the scatter plot to see if there is a possible linear trend. The correlation coefficient and residual plots can also help determine whether the linear model makes sense to use to estimate the situation. In some cases, another type of function might be a better fit for the data, like quadratic or exponential or trigonometric. Or the two variables you are examining may be uncorrelated, and you should look for other connections using other variables. So, the summary shows that the sign of R, which is the correlation coefficient, is the same as the sign of the slope of the best fit line. The values for R go from -1 to 1, inclusive of those endpoints -1 and 1. The closer R is to 1 or -1, the stronger the linear relationship between the variables. And the closer R is to 0, the weaker the linear relationship between the variables. In this activity, you are given 8 R values or correlation coefficients and 8 scatter plots with linear models. So the first two are shown here, and on the next slide, you'll see the remaining 6. What you are asked to do is to take each R value and tag it to one of the 8 scatter plots. You will need to use your extra file of information or slides in order to do this, or go ahead and pause the video or move the video to the next page, then pause it, identify all the R values, and then unpause it to see your answers. Here is the remaining 6 scatter plots. So between this slide and the one previous, go ahead and pause the video, try to do the match of the scatter plots and the R values, and then I will go over the answers. All right, your answers are as follows. Model A on the first page was a very strong linear increasing relationship. So that one was an R equals 1, which was the 8th R value in the list. The graph of B was an increasing linear model, but was not really, it was strong, but it wasn't as strong as the first one. That was a value of R equals positive 0.9. And that one was number 7 in the list. All right, for the graph of C, this is a decreasing strong linear model. This is R equals negative 0.95. So it's strong, but it's not as strong as down here in F. F is the best linear model that's negative or decreasing, and that's an R of negative 1. So C goes with the value number 2 in the list, and F goes with the value number 1 in the list. All right. For D, it's also a decreasing linear model, but it's not quite as good. This is R equals negative 0.74, which this one was number 3 in the list. E, an increasing but not that strong linear model. It's still pretty strong, but not as great as A or B. So this one was a value of R equals 0.65. And that one was number 6 in the list. And G was not a strong model at all, although it's decreasing. That is R equals negative 0.06. You can see how close to 0 that is. And that one is number 4 in the list. And lastly, we have another increasing model. So this is a positive R, but it's not nearly as strong as the others, and it's 0.48. So kind of midway between 0 and 1. And this one was number 5 in the list. Hope you did well on that match. In this activity, Jada wants to know if the speed that people walk is correlated with their texting speed, or their ability to text while they walk. To investigate this, she measured the distance in feet that 5 of her friends walked in 30 seconds and the number of characters they texted during that time. Each of the 5 friends took 4 walks for a total of 20 walks. So you'll see we have 20 data points here. So, for example, this is one ordered pair. This will be your x1 variable, and this will be your y1 variable. Here are the results of the first 20 walks. So there's 20 ordered pairs. What you're going to be asked to do is use Desmos or any other graphing technology in order to create a scatter plot with this data. And then once you've got the scatter plot, you want to use the technology to find an equation of the line of best fit and also look at the correlation coefficient. Then we're going to have another data set. So go ahead and pause the video here and write down this data, and then we will go over what you found later. And this is the second data set of data. Over the next few days, the same 5 friends practiced walking and texting to see if they could walk faster and text more characters. So they practiced before this data was collected. They did not record any data while practicing, but after practicing, each of the 5 friends took another 4 walks. And here are the results of the final 20 walks. So once again, we have an ordered pair. This is your, we'll call it x2, y2. And we have 20 more ordered pairs. So now you want to open a new Desmos or graphing technology file, enter this scatter plotted data, and calculate the line of best fit and the R value for this data. We'll call this data set 2. Go ahead and pause it here and do that. All right, here are the two data sets. So the first data set is without practice, and the second data set is with practice. So what do you notice about the two scatter plots? What I noticed is they are both fairly linear, although the first model is a stronger correlation. They're also both decreasing. So like I'll draw in a line of best fit through this one and maybe through this one. I'll write down for you the two line of best fits. So in the first model, we have y equals negative 0.85. So you can see the negative slope, x plus the y-intercept of 218.61. And in the second model, we also have a negative slope, negative 0.47x, so it's not quite as steep, and a y-intercept of 222. So the y-intercepts are very close, 0.17. The first model's R value is negative, because it matches the slope, 0.95. And the second R value is negative as well, but it's not quite as good of a linear fit. It's negative 0.68, so not as close to -1 as the first data set. So Jada noticed that her friends walked further and texted faster during the last 20 walks than they did during their first 20 walks. So did you see the scale differences? This one gets to 180 distance, and this is 240 feet. So in the second data set, they definitely went faster or further. And the number of characters text, it goes up to 200 in the second data set, but only 150 in the first data set. So the practice paid off. But notice that it's not as good of a linear fit. So since both were faster, she predicted that the correlation coefficient of the line of best fit for the last 20 walks will be closer to -1. She was clearly wrong. It was not as good of a linear model with the practice. So now we've found the line of best fit and the correlation coefficient. Why do you think the correlation coefficients for the two data sets are so different? Explain your reasoning. Well, the data in the second is much more scattered, where the practice probably helped some people more than others, but even with the practice, they weren't quite as good. So it actually had more varied results, where without the practice, the folks that were walking further were not able to text as well as the ones that didn't walk as far. All right, so that's it for the lesson. Go ahead and try your homework.